All right. So we were talking about now that you've started with the methyl ketone and thought backwards to what the beta keto ester must have been, now we need to think from this alpha dialkylated beta keto ester back to our beta keto ester starting material. We're going to start with actually not the ring example because we don't want to go too evil too quick. So let's finish this example. This is a single, just monoalkylated beta keto ester. We thought backwards from this enol to now this beta keto ester. And I'm asking you to think backwards one more step. Guess we need to slide some things over maybe just a little bit. Here's the starting material. What was the alkyl group that got added to the alpha carbon? Well, you do this is you find the alpha carbon of the beta keto ester, draw a squiggly line between that alpha carbon and the stuff that it's attached to. Count the number of carbons on the other side of that squiggly line. There are 3. 1, 2, 3, and then on the end of that, you needed a leaving group. Chloro, bromo, some good leaving group. Okay? So for fun, this is fun, right? For fun, let's write out that synthesis in the forward direction then. Through the looking glass now, going now forwards. It's tough to keep track of when you're thinking backwards versus thinking forwards. This is now the starting material. How do I get that alkyl group on there? What am I going to do? Deprotonate it first. I can use a cheap and easy to get base. And then in a second step, I'm going to use this alkyl halide, my 3-carbon alkyl halide. Then I'm going to draw the monoalkylated beta keto ester. Carbonyl carbon, alpha carbon, beta carbon. This is the alkyl group that I just attached. Now, I'm going to do acid catalyzed ester hydrolysis, decarboxylation, and tautomerization. If I want, and I'm good at this, I can skip ahead all the way to the product, which is this. Understanding that this portion of the molecule stays unchanged. What changes in the next step of ester hydrolysis, decarboxylation, and tautomerization essentially just removes this part of the molecule. But if I want to draw intermediates along the way, after ester hydrolysis, I have the acid. After decarboxylation, I have the enol. And except that's not an enol. I have the enol, and then after tautomerization, I have the methyl ketone product. So that's hydrolysis, decarboxylation, and tautomerization. That's thinking forwards. right? Let's do the next one. Before we draw the forward synthesis, let's think backwards to the beta keto ester. Okay, and then the starting material would have been the acetoacetic ester. To identify what alkyl group or groups I must have added, find the alpha carbon, draw squiggly lines between the alpha carbon and the alkyl groups on it, and then that will tell you which alkyl groups you must have added. 1, 2, 3 carbons, alkyl bromides, alkyl chlorides, alkyl iodides would have been okay. So as an exercise, we won't do this now, but you should, after class, draw this synthesis in the forward direction. And I'll update the notes so that it's there and you can go check your answer. Finally, challenge unlocked. Let's deal with the horrible, terrible example. We're thinking backwards to the beta keto ester that's apparently dialkylated, and we're thinking backwards even further to the acetoacetic ester starting material and whatever else that should have been. Again, we can use our squiggly lines to disconnect the blue alpha carbon conceptually from what we must have added. I see 1, 2, 3, 4 carbons there. Carbon 1 is attached to the alpha carbon, so is carbon 4. What do you think I added? I needed a 4 carbon chain, and what's on either end of that chain? Got to have leaving groups. Okay, bromides, iodides. So let's actually draw that out in the forward direction, and this will be how you make a 5-membered ring. Notice that of that 5-membered ring, 4 of the atoms come from this portion, and then the other atom of the ring comes from the alpha carbon of your beta keto ester. All right, so drawing this synthesis out in the forward direction, we'll start with that acetoacetic ester. We'll deprotonate it with our cheap and easy to get base, sodium ethoxide. And then we're going to use this 4 carbon bis or dihalide. 1, 2, 3, 4 carbons and halides at either end. So this is going to deprotonate at the alpha carbon, and that's going to give me the resulting enolate is going to attack one of these 2 carbons in SN2 fashion, making a new bond between the alpha carbon of the enolate and then one of the carbons of the alkyl halide. I'm going to say carbon 1 just for fun, but the 2 carbons are equivalent, so you can't actually tell. 1, 2, 3, 4. And then the other end of that is still going to have a bromo group on it. Questions about that step? Okay, then we'll do, again, another deprotonation reaction. I'm going to actually draw the intermediate. I'm going to number the carbons. And then we'll do the intramolecular SN2 reaction, where the lone pair on the blue alpha carbon attacks the carbon bromine sigma star on orange carbon 4, kicking off the bromine. So now the alpha carbon is going to be bonded both to carbon 1 and to carbon 4. The way you do this is you draw the alpha carbon, you draw the bond to carbon 1 and the bond to carbon 4, and then you realize that carbons 1 and 4 are connected by carbons 2 and 3. You draw 2 and 3 right there. And then before you know it, without even trying, you drew a pentagon. Yeah.
Is there competition with nucleophilic attack from the ethanol or ethanoate?
Good. Yeah, good question. Is there competition between nucleophilic attack by this sodium ethoxide, the alkoxide ETO-, and the alkyl halide? No. Well, actually, not at this stage, because you just remove the proton. Here, I think you're seeing, yes, the ethoxide could either remove this proton or it could do SN2 chemistry on the bromo. I think the idea is this proton is acidic enough that it intercepts this base before it can do nucleophilic attack. Probably reflecting the fact that acid-base chemistry proton transfer is faster than attacking carbons. Yeah.
On the first example, in the first synthesis, we only had one equivalent of the alkyl bromide.
Right.
Why wouldn't that attack again to get something more close to that?
We could have chosen for that to happen, but the point is that when we use this base, removal of this proton is 100% in a single step. And then, only then, do we add the second alkyl group. You are right that there is still an acidic proton there. If we so choose, we can remove it and alkylate again. We just didn't in that example. But it's not going to happen on accident, because it can't happen unless we remove the proton. Okay, good. Other questions? All right, so coming full circle, we'll use water, aqueous acid, and heat. Remember, when you do that, if you want to do it, conceptually think all in one fell swoop, you just draw a squiggly line between the alpha carbon and the ester. Everything on the other side of the line with the ester goes away. Everything on this side of the line, opposite of the ester, stays. So our final product is going to be this methyl ketone, of course, CO2 left. If you want to go back along the way and draw the intermediates after ester hydrolysis, decarboxylation, and then tautomerization, you can. All right? That's probably going to take some practice. We've gone through it a couple times, seen it through in a couple different perspectives. Probably you should practice that. One thing I'll point out is that your text says you can do this kind of thing not only with acetoacetic ester as the starting material, but also this molecule, which is called malonic ester. The only difference between malonic ester and acetoacetic ester is malonic ester is a beta diester instead of a beta ketoester. But you still have a carbonyl carbon, an alpha carbon, and a beta carbon. So you can do similar things with the malonic ester. Let's just do a monoalkylated product. Let's just, for fun, use we like 3. Let's use a 3-carbon alkyl bromide, except that needs to be the second step, sorry. We'll use a base to deprotonate. The pKa of a proton alpha to 2 esters is around 13. That's enough for 100% deprotonation, followed by SN2 reaction, alkylation on the alpha carbon to give you this molecule with 3 carbons. Okay. I'll walk you through we won't draw the mechanism, but I'll walk you through the ester hydrolysis stage. We have 2 esters. Acid catalyzed conditions are going to hydrolyze both of them. So now you're going to end up with this beta diacid after ester hydrolysis. As with any kind of beta keto carboxylate compound, you can do decarboxylation. You may be asking at this stage which one of those comes off as CO2 and which one stays. It doesn't actually matter, you can't tell. For our purposes, we'll call this one the beta sure. So decarboxylation is going to proceed analogously to how we've shown it before. I'll draw for you the sort of enol product. There's the CO2 that leaves. And then after tautomerization, you go from this enol form to the acid form that looks like this. And at this stage, these are the carbons that are all still in the product from this earlier intermediate. So if you see an alpha alkylated carboxylic acid, that is some carboxylic acid with an alkyl group on the alpha carbon, you can think that you can be thinking, I could have made that using the malonic ester as a starting material. Yeah?
This is done in the lab. What's the acid catalyzed user?
What's the acid used to make this process happen in the lab? Good question. And it's probably not sulfuric acid because yeah, it's a good question, and I don't know. We need to look up a synthetic procedure.
This is not a very common reaction then.
No, well, I mean, actually, people use it. I think they've done it in Professor Castle's lab. It just sort of depends on the project that you're working on and what the strategy and goals are. My guess is that if you're using an aqueous acid, you're probably using HCl to start with, and perhaps perhaps catalytic sulfuric acid, but not at a really high concentration. There's lots of other things that can happen when you use sulfuric acid. So yeah, it's a good practical question, and I'm sorry I don't have a great answer to it. All right, others? Okay, so I kind of want to show you some biochemistry and biology involving decarboxylation, but there's kind of a whole other reaction that's in this chapter that we need to talk about, and we maybe spend a little too much time on decarboxylation. So I'm going to hold off on that for now. What we've done so far has all been alkylation, or adding alkyl groups to the alpha carbon of various carbonyl compounds. We did direct enolate alkylation, and then we've sort of used this sidestepping alkylation followed by decarboxylation and so on to avoid some of the practical issues that come with direct alkylation. We're sort of shifting gears to talk about adding now here no longer alkyl groups, but halides to the alpha carbon. So this is called alpha halogenation of carbonyls. There's quite a bit we could say here, but I'm going to limit it to one specific reaction that's described in your text, which is alpha halogenation of carbonyls under acidic conditions. Again, there's more that we could say. You can do this reaction under basic conditions. It gets a little complicated though, and the payoff isn't necessarily worth the investment in terms of our time and whether or not it's worth knowing something. So here is just a regular ketone. Our solvent, you need an acid, and in this case, your acid is the same as your solvent. This is acetic acid. Acetic acid is relatively inexpensive. You can use it as a solvent. It also is important for the reaction. And then your other reagent is bromine. The impact of this reaction is to install one bromo group on the alpha carbon. So, theory doesn't need to be involved. There we go. So let me show you mechanistically what's going on. Under acidic conditions, we're likely forming the enol. So we're going to use the acid, which I'm going to abbreviate as just HA, to protonate the carbonyl oxygen to turn it into the oxonium ion. Doing that makes the alpha carbon much more acidic. Normally the pKa of the alpha carbon of a proton alpha to a ketone is in the 20s. But in the same way that protonating a carbonyl makes the carbonyl carbon easier to attack and more electron poor, protonating the carbonyl oxygen also makes the alpha proton much more acidic. So now even the conjugate base of our acid can remove the proton from the alpha carbon, and that actually finishes tautomerizing to the enol. At this stage, we're going to use the enol as a nucleophile. And we're going to reflect on the fact that you could draw a resonance structure of the enol that would look like this, where the alpha carbon, the one that's involved in the double bond, actually has a negative charge on it. So even though you might be tempted to look at the enol and say, oh, if the enol is a nucleophile, it should be the lone pairs on the oxygen that are reactive, it turns out that enols are nucleophilic on the alpha carbon because of resonance. We've drawn this resonance structure, which shows you that the lone pairs on the oxygen are actually also delocalized onto the alpha carbon. So with that in mind, it's not such a stretch to have the alpha carbon attack the electrophile, which here is bromine. So lone pair electrons on the alpha carbon attack the bromine sigma star, thereby breaking the bromine bond and making a new bond between bromine and the alpha carbon. Then our final step will be to restore the acid by removing a proton from the oxonium ion, and that gets us to our product. This is now an alpha halo or alpha bromo ketone. Okay, questions about that? So why are we doing that? That actually converts a carbon, swaps out a carbon-hydrogen bond for a carbon halide bond, and carbon halide bonds are useful. You can use them in subsequent synthesis reactions, basically with chemistry that you learned how to do in 351. So let me give you a few examples, and I'm always looking to up the evil scale, mostly to prepare you for future complicated situations that you might find yourselves in on exams. Here is bromine, here is acetic acid, which catalyzes the enol formation. Here's the alpha carbon. This alpha halogenation of ketones will install a bromo group on the alpha carbon. Now we're going to consider some things you could do with that bromo leaving group. For example, one of the classic things you could do would be an SN2 reaction. So some nucleophile attacking the carbon bromine sigma star to give you a new bond between the alpha carbon and whatever your nucleophile is. So just for an example, let's choose this thiolate, to negatively charged sulfur, as a nucleophile. Okay? So your task is looking at something like this product and saying to yourself, this looks like something that could have been a nucleophile. And it could have had a halide leaving group there to begin with. How could I have gotten that halide group there? And then you would need to remember, oh, I know a reaction that actually puts a halide on a carbon alpha to a carbonyl. Again, synthetically thinking backwards. SN2 is a reaction you learned in 351 that you can do with alkyl halides. What about elimination reactions? Doing an E2 reaction. I need a little bit more space, so I'm just going to slide this down a bit. If you were in 351 and you wanted to do an elimination reaction, you would have used some kind of base that's not a good nucleophile. We'll call this a non-nucleophilic base. There's one that you probably memorized in 351. This was potassium tert butoxide. There's another one that is inconveniently just sort of dropped on you in this chapter that your text will use. I'm talking about it now not because it's particularly important, but because you will see it in practice problems. Your text uses the base lithium carbonate as a non-nucleophilic base. Carbonate, and actually, yes, there are 3 oxygens. looks like this. Lithium is the counter ion. I believe that your text, I'm trying to remember, but I believe your text uses the combination of these two reagents, lithium carbonate in combination with lithium bromide. Your text provides no explanation as to what the lithium bromide is for. I am sorry about that. I don't have an explanation for it either, but you can think of carbonate as simply a non-nucleophilic base. Something that's not going to do substitution chemistry. Likely what's happening is the author of your textbook is following an actual paper from the literature, chemical literature, where they did this reaction, and these were the conditions they used. You would have to go back and find that paper and figure out whether the authors even say why they use these conditions. Sometimes when people are discovering new reactions, they try something, it doesn't work, they try something else, it doesn't work, they try something else. Yes, it works, and then they move on because it works without interrogating in too much detail why it works. Other times they're like, it sort of works, but we want it to work even better, so let's add some other things. Likely what happened in this case is the reaction worked better when they used this base, but then they also used what's called an additive. They added lithium bromide, and again, I'm not sure why. In any case, if you were going to do an E2 elimination reaction, you're looking for protons that are beta to the leaving group, and the only ones you have are here, right? So the product of the E2 reaction, the elimination reaction there, and this is a review of 351, would be this molecule, right? Where a base removed the beta proton and kicked off the leaving group. Okay, so why are we bothering with this? Well, that product of eliminating the alpha halo carbonyl compound is interesting because this is an alpha beta unsaturated carbonyl compound. And we have used that in chapter 13 as a starting material. Just to review, in chapter 13, we learned that if you take this molecule and react it with lithium aluminum hydride, you can reduce the ketone to an alcohol without messing with the double bond. We learned in 351 that you can use hydrogen and palladium on carbon to reduce the double bond without necessarily hitting the ketone. We learned in chapter 13 of 352 that you could use an organolithium reagent or a Grignard reagent to do 1,2 addition of the nucleophile to the carbonyl carbon. And we learned in chapter 13 of 352 that you can use cuprates to add the nucleophile not to the carbonyl carbon, but to the beta carbon. So that's sort of a review of a lot of things thrown at you all at once, but it's larger synthetic pathways that are now enabled by the fact that we can put a halide on the alpha carbon. Yeah?
I had a question about hydrogen palladium bond reactions.
Okay.
Can that not produce the CO double bond?
Yes, it can. Hydrogen and palladium on carbon can reduce CO double bonds. I also know by experience that you can run the reaction under conditions that reduce the carbon-carbon double bond, but not the carbon-oxygen double bond. probably this reflects the fact that carbon-oxygen bonds are more stable than carbon-carbon double bonds. In fact, because of that confusion, I never teach in 351 about reduction of carbonyls using palladium on carbon. Some do. To avoid that confusion, I will just erase this example. I'm never going to ask you to reduce a ketone using hydrogen and palladium on carbon. Some of my colleagues may disagree. I respect them. They respect me. We're all okay. What else? Yes?
I've seen examples in the textbook where we either end up with more or less substituted elimination product is using, I think, the same reagents. I'm not sure if there's a specific context in which
You're talking about elimination reactions in more or less substituted elimination products. Of course, here, there's no choice. There's only one kind of beta proton.
if there's another alkyl group, for example, next to it or something like that.
If there were another alkyl group, presumably you would follow the same pattern you used in 351, where the more substituted alkene would be the major elimination product. Yep. Okay, others? Oh good, we have time for biology now. All right, I want to show you a couple of decarboxylation reactions that are going to be involved in your future. We're going to talk about metabolism later on in this class, so what I'm doing now is a preview. I'm trying to connect in what we're learning now to something we're going to learn in the future. The first is a long time ago, at the beginning of class, I told you that acetoacetic ester was masked acetone, and that through decarboxylation we could get to this product. Nature uses beta keto or carbonyl compounds sometimes as what I'm going to call masked enolates. So in fatty acid synthesis, there is, we'll just put an R group here. This is called a thioester. And this is called malonyl CoA. It's actually coenzyme A on the other side of that thioester. But this is basically a beta keto acid. Here's the carbonyl carbon, here's the alpha carbon, here's the beta carbon. And as such, you ought to be able to think of this, look at this and say, okay, I think this portion is going to come off as CO2, and this is the bond between the alpha carbon and the carbonyl carbon. This is the bond that's going to break, and this is what's going to be left when it breaks. And what would it, if the electrons on the oxygen kicked down and kicked off the green group, what would it leave as? And the answer is it would leave as an enolate. So sometimes when nature wants an enolate, it will bottle the enolate up and mask it as this beta keto acid, which then when it gets to an enzyme active site can undergo the decarboxylation reaction. So what I'm going to show you now is a step that happens in fatty acid synthesis. The decarboxylation happens and you end up with the enolate. All of this in an enzyme active site. And then over here, you have some other thioester. I know there's lots of R groups here, so just ignore them for now. In an enzyme active site, this enolate will actually attack the carbonyl carbon to make a tetrahedral intermediate. That's this kind of thing, an enolate attacking a carbonyl carbon. That's the stuff of chapter 18. We're not going to talk about that today. That's a preview. But the point is that nature uses decarboxylation to generate an enolate, which it can use as a nucleophile. In fact, most of the time people will not bother to draw the enolate on its own. Instead, most people will draw, as the carboxylate group is kicking the enolate off, it will show the electrons in this carbon alpha carbon bond going directly to attack the electrophile. Okay, it's all right if you don't understand this step yet. It's not that hard. You actually should sort of be able to follow it. Ketones, carbonyl compounds are electrophiles, enolates are nucleophiles. But the point is we're using decarboxylation to make the alpha carbon supernucleophilic so it can do chemistry. All right, and then questions about that? The next thing is another decarboxylation reaction that happens in the generation of histamine. So what I'll show you here is I want you to understand, basically, I want you to understand the ideas and the chemical steps without memorizing structures. What I'm drawing for you now is the amino acid called histidine. And there is a process involving an enzyme that is called a decarboxylase. And it's going to use the cofactor pyridoxal phosphate. It gets rid of CO2 from histidine, and what you're left with is this molecule. This portion is what leaves as CO2. Everything else stays in place, and this is called histamine. And if you take antihistamines to prevent allergies, you're trying to prevent the synthesis of this molecule, or trying to prevent the signaling of that molecule. Not sure, don't understand the medicine. All right. PLP you've seen before. This is pyridoxal phosphate. It's an aldehyde, and it forms imines, A-I-M-I-N-E, an imine with amino groups. So here's the aldehyde. Let's see, that carbon should have been a nitrogen. Methyl group there. So PLP adds to the nitrogen of histidine to form an imine. So let's draw that imine. For now, I'm just going to show the histidine side chain as an R group. Here is the imine that forms with PLP. And the idea here is that if you squint, this looks a little bit like a beta keto acid. Carbonyl carbon, alpha carbon, beta position with a double bond to some atom there. Not exactly the same situation, but this is what sets us up for the decarboxylation reaction. All right, I could show you the decarboxylation reaction. That may be enough today. Maybe I'll show it to you at the beginning of next time. Let's just be done. Have a good Monday, and I will see you on Wednesday.